to have Professor Goyal with us from Boston University, who will talk about improving imaging on photon and electron level, one click at a time. As always, please mute yourself and unmute as you see fit to ask questions. We don't control that. Thank you very much. Vivek, it's all yours.
Okay, thank you. Thank you, Wojtek, and thanks to the whole FFT team for arranging the seminar. I also heard that there was publicity through the IEEE Signal Processing Society Washington chapter. So whatever brought you here, thank you for joining. My goal in the talk is to explain some ideas around probabilistic modeling of single photon and single electron detection. And then if I'm successful, I'll surprise you with the sorts of improvements that can come from this fine-grained modeling. I'm splitting the talk between photons and electrons. In the first part, I'll talk about active depth and reflectivity imaging based on single photon detection. And then in a second shorter talk, I'll talk a little bit about particle beam microscopy modeled at the level of counting secondary electrons. Each part has some related stories, but I'll go over those very quickly. So to start with, here's an ordinary digital photograph of Marsh Plaza at Boston University. How many photons do you think were detected by the camera to produce it? If I had taken the time to set up the Zoom as I would for my teaching, I might have set up a survey question here. Whoops, I actually clicked ahead without giving you a chance to think about your answer. So it's a lot of photons, and I don't really know the answer, but I have at least a plausibility argument for the choice of 4 times 10 to the 12. I can get about 4 times 10 to the 12 as a product of illuminance on an overcast day, the aperture area, the photons per second to produce a lumen, the exposure time, and the detection efficiency. So a plausibility argument for 4 quadrillion photons. If the photo is 4 megapixels, then this works out to be 1,000,000 photons per pixel. That's a very different setting than what's of interest to me today. So first, it's a lot of detected photons, so it doesn't seem to matter whether you've kept track of them individually. And second, and a bit more subtle and less important, the sensor response to the photons is essentially linear. So again, there's no motivation to think about the photons as discrete. Today, we're going to pay attention to every click. And in part 1, the clicks are caused by individual photons. This is in the context of active imaging with pulsed illumination, also known as direct time-of-flight lidar. And we're going to go down way below 1,000,000 photons per pixel, down to 1 photon per pixel. So first, to give a quick sense of how lidar works, suppose that we have a pulse-directed light source, then several properties can be inferred by the relationship between the transmitted pulse and the received pulse. The time shift is called the time of flight, and it reveals the distance. The baseline offset tells how much background or ambient light is present. And the amplitude of the received pulse over the background gives the reflectivity. So we can scan the light source over the whole scene to give a measurement separately at every pixel and have a depth image and a reflectivity image. So that's the way direct time-of-flight lidar works, roughly speaking. LiDAR has lots of applications from A to Z, and one of the very hot applications at the moment is autonomous navigation. LiDAR is also embedded into Apple's iPad Pros and the current or next generation of iPhones, so I could also draw attention to augmented reality as a key application. The design space is very complicated with issues like eye safety, range, transverse resolution, longitudinal resolution, etc. Today, I don't want to talk about all these trade-offs. I want to concentrate on how to make the most of whatever data is collected. So let's talk about modeling and methods for 1 click per photon. We have a pulsed light source that we're going to raster scan. The illumination of one small patch at a time, indexed by ij, is what's going to create the transverse spatial resolution. And here in several of the slides, I'm going to include device specifications for a set of experimental results that I'll show. But I'm not going to talk about the specs because I want to concentrate on the concepts. And if you're more mathematician than engineer, feel free to just completely ignore all the specs and just think about the concepts that we want to introduce. Okay, Zoom creates some extra delays, so I don't want to click too far. Okay, so we have the pulse-directed light source, and then we want to detect the reflected light with single photon sensitivity, and we do that with a single photon avalanche diode. To record the times of the photon detections with high resolution, we use a time-correlated single photon counting module. Now, an unstated assumption in most of the work in single photon lidar is that a histogram of detection times over many repetitions is treated as a proxy for the analog waveform of the earlier discussion. It's in discrete time because of the finite resolution of the time tagging, and it's noisy. But the concept of a histogram seems really silly if you only have a handful of detections. So I want to argue that even though the amount of data that you collect can be so low that it seems silly to create a histogram, you actually may still have enough information to form accurate depth and reflectivity images. Okay, so like I said, one of my points here is that it's not unreasonable to get by with fewer photon detections than are needed to form a reasonable histogram. And we're going to take it all the way to the extreme of just 1 photon per pixel. Time-correlated detection puts the illumination and detection waveforms on a common time axis, except we don't really have waveforms anymore. From the quantum nature of light detection, what we're actually seeing is an inhomogeneous Poisson process. The rate function of the Poisson process in the absence of background is a scaled and time-shifted version of the illumination waveform. It has a time shift depending on the depth Zij and amplitude depending on the reflectivity alpha ij. All right, the contribution from background light and dark counts is a homogeneous Poisson process. And so what we really observe is the merger of these two Poisson processes, adding together the background and the response from the scene. Not every illumination light pulse is going to generate any photon detections. So suppose there's no detection from the first illumination repetition period. Maybe there's also no detection in the second period as well. And in the third period, here I've marked a detection at a relatively likely time. I'm calling it relatively likely because the yellow flux waveform is relatively high. There could be a detection at a relatively unlikely time, marked in blue, as if we knew that that detection was due to background. But we don't actually know whether a photon that we've detected is due to light that's back reflected from the scene or ambient light. That's part of the actual problem. You don't know if the rate function is like what we see here, or the rate function is a shifted version of that. That's part of what we're trying to infer. And it seems like that's going to be very difficult to do from a single detection. Of course, it is extremely difficult to do from a single detection, but we're going to model the response appropriately and then exploit spatial regularization and find that a single photon per pixel is enough to form interesting images. All right, so we're detecting only one photon per pixel. What is the distribution of the time of the single detection? From the Poisson rate function lambda, we get the PDF shown on this slide. When the incident flux is large, there's a significant shifting of the peaks and other waveform distortion. We're going to completely put that aside for now, but it arises again later in the talk. For now, let's assume that lambda of t is small. Then we can approximate the PDF as defined on each repetition period as a scalar attenuation of the flux waveform with geometric decay over the periods. With this, we end up with a beautifully simple model for the data by looking at U, the detection time, divided by the repetition period and the remainder from that division. So we have one photon detected at pixel ij. From the time of that one detection, by dividing by the repetition period and looking at the remainder, we have a discrete random variable kij of the number of pulses until that one detection, and a continuous random variable tij of the detection time relative to that last pulse emission. Kij has a geometric distribution that encodes the reflectivity alpha ij in the sense that it has a parameter that's in a one-to-one correspondence with alpha ij, assuming that you know the signal strength S and the background strength B. Similarly, Tij encodes the depth Zij. Each Tij has a PDF equal to a normalized version of one period of the pulse plus background rate function that I've been depicting in yellow on these slides. So we can now hope that with these models for the measured quantities, we can exploit some reasonable model of nearby pixels usually having similar depths and reflectivities, and that this will be enough to solve an inverse problem. So it turns out that nature's been kind to us in that the negative log likelihood of Kij is convex in alpha ij, and it has no dependence on the depth Zij. Nature's less kind in the Tij distribution. If there were no ambient light at all, and under reasonable approximations for the laser pulse shape, we would have convexity of the negative log likelihood, but as it is with any significant amount of ambient light, we do not have convexity. So the image formation method that we developed follows a three-step procedure. First, we compute a regularized maximum likelihood estimate of alpha, exploiting convexity and adding a convex regularizer. Then we'd like to be able to make believe that there's no ambient light. So we have a step where we try to guess which photon detections are due to ambient light and which are due to the back reflected light from the scene, so that we can throw out or censor the detections that we think are due to ambient light. If we do a reasonably good job in that second step, then we can make believe that there's no ambient light to get a convex regularization to solve, a convex optimization problem to solve for regularized maximum likelihood estimation of the depth. So let's see what we get with that. Following the data collection protocol that I've described, we're aiming our laser at one patch at a time and just detecting one photon before we move on to the next patch. We did our experiment here where half of the detected photons are due to ambient light to kind of push the limits of how well we can perform that noise censoring and still get high quality results. So here's raw reflectivity information overlaid on a 3D point cloud. Again, I forgot that, whoops. I forgot that while using Zoom, the videos behave differently. So this model should rotate, but it's not that important here. This is a depiction of the raw data, essentially, where from each photon detection, we are getting an initial estimate of depth and reflectivity. So the result of the first step is just regularized maximum likelihood estimation of the reflectivity, not changing the depths at all. And I've used these videos over Zoom before, but not had this problem before. I'm not sure why they won't. Huh. Okay, for some reason, the video is not, at least from my view of it, the video is not running. It's just showing me one of the frames from the video. The view that I have right now myself, it is showing you the result of the result of step 2 now, which is the result of attempting to censor the photon detections that are due to background light. And so so from the first step, there was reasonable denoising of the reflectivity. In the second step, we see that detections have been removed from all the parts of the scene where there actually was no object. So whatever was detected was actually from ambient light. And then we can see that the mistakes in the censoring are happening mostly around the boundaries of the object in the scene. And that's because the censoring technique is trying to exploit correlations between a pixel and its neighbors. And now, okay. Well, I'd like to be showing you this 3D model rotating, which is the result of the third step, our final reconstruction, which is applying regularized maximum likelihood estimation to the depth after that noise censoring step. So even though I've at least 3 different times I've used these videos in a remote talk, but it's not working.
Vivek, if you reshare, there's a checkbox from your desktop Zoom.
Yeah,
you can optimize for video, and would that be better?
Yeah, you know what? I think this is the last video anyway. It doesn't really matter. But I know it. Thank you, Min. Right, the optimize for video choice. Maybe that would have mattered here. Maybe I had it by default in other cases. This is one of the final frames of this third video anyway. So this is a depth and reflectivity reconstruction that's been formed from one detected photon per pixel. Of course, you can't do this where half of the detected photons are due to ambient light. You can do this well because you're exploiting the assumption of piecewise smoothness of both depth and reflectivity. And that assumption of piecewise smoothness is being exploited through through total variation regularization. So along these lines of observing small numbers of clicks and making reflectivity and depth estimates, I've gathered some examples where the first row shows conventional processing of some data, and the bottom second row shows what we obtain with the same data. What I was describing here was what we call the first photon imaging method, which can be effective down to a signal to background ratio of about 1. So there's 1 photon per pixel, and about half of the detected photons are due to signal light. So I call that half a signal photon per pixel and half an ambient light photon per pixel. We subsequently looked at related problems that are more challenging in a variety of ways. Using a SPAD array makes it inevitable that the time resolution will be coarser. In this case, it was 50 times coarser, changing from a time resolution of 8 picoseconds to a time resolution 50 times coarser. Not a state-of-the-art SPAD array, but what we had available at the time, with about twice as much signal and the same big signal to background ratio, we get reasonably good results. We also looked at withstanding much more ambient light. Here, there's 25 times more ambient light, and Josh Rapp introduced several ideas to deal with that. Earlier this month, Josh was awarded a 2020 IEEE Signal Processing Society Young Author Best Paper Award for this work. And the fourth column shows imaging through a partially transmissive scatterer. These are by no means the only results of this type, just a sampling of my own results. Getting by with the smallest number of photons or the smallest signal to background ratio has been a fun pursuit, but it isn't the only issue in direct time of flight LiDAR. So I'm going to change gears, still talking about direct time of flight LiDAR. Let's consider an automotive use case for LiDAR. So there, sure, we definitely want to be able to see weakly reflective objects that are very far away. So we do have motivation to want to get by with small numbers of photons. But some objects are near and highly reflective, and they may even be retroreflective, like a road sign or a road marker. So in that case, we need to be able to handle very high dynamic range of incident photon flux. Within our field of view at any one time, 1 pixel, there may be very strong return, and another nearby pixel maybe has a very weak return. Handling strong signals actually requires an understanding of dead time effects in the detectors. And this is all, it also invites us to introduce some new mathematical modeling. So we've discussed incident photons as arrivals in an inhomogeneous Poisson process with a rate function that's proportional to the incident photon flux or intensity. We could add another detail to our model in terms of the detector having efficiency strictly less than 1. This means that generation of photoelectrons can be modeled as the results of independent biased coin flips at each photon incidence. This kind of thinning of an inhomogeneous Poisson process is equivalent to multiplying the incident intensity by a scalar, so it isn't actually very interesting. Things get interesting when we include the dead time of the detector. Each photon detection results in a dead period, which here we've denoted by T sub d. For a SPAD detector, this is the time to quench so that the sensitivity can be restored. You see from this example that photons that arrive too close together cannot be detected. And what's illustrated is a free running mode without periodic resets. A time-correlated single-photon counting module also has an electronics dead time, which here is denoted by T sub E. If that electronics dead time exceeds the detector dead time, TD, then it's also significant and causes missed clicks. I mentioned the electronics dead time just to kind of hint at some of the depth of the complexities. And because we have included the electronics dead time in our latest analytical and experimental results. But I'm going to ignore it here to just give a simpler explanation and give a hint at how we model the dead times of the detector and take advantage of having that accurate model to improve our estimation performance. Even when I ignore the electronics dead time and consider only detector dead time, the effect is really far from obvious. So what's illustrated here by the red curve is the incident light in a simulation described by a Gaussian pulse centered at 40 nanoseconds plus some moderate background. So think of that as representing a direct time of flight LiDAR experiment with a Gaussian illumination pulse and an object that is at a time travel of 40 nanoseconds. Okay, then what's shown in blue is the detection time histogram that results from the repetition period being 100 nanoseconds, the detector having a dead time of 75 nanoseconds, and also the illumination pulse width is 2 nanoseconds. So we can, from the detection time histogram in blue, we can guess that there's an object at about 40 nanoseconds time of flight. Actually, the peak has been shifted. I mentioned earlier this concept of the peak shifting a little bit because you're looking only at a first detection time. So the peak has been shifted to a little bit earlier time, but there's also a bunch of other strange things going on here. What would we make of this this kind of secondary bump around 20 nanoseconds? Like, how should we interpret this data? I mean, I guess I'm imagining that we'll interpret this data naively because I'm going to show you how when you include the dead time within your model, that kind of bump is totally explained. But if you don't understand dead time effects, you might think that there's something partially transmissive at about 20 nanoseconds worth of distance. That's certainly possible. There may be some fog between you and the object that's at 40 nanoseconds, since the secondary peak is quite broad. Or maybe the breadth of this secondary peak actually suggests that it's an aliased component coming from around 120 nanoseconds, but aliased back to around 20 nanoseconds. That's also possible. And these are all reasonable interpretations, even when the scene is so simple, having just a single reflector. So because of this kind of complexity in the measured data, it's worthwhile to carefully consider dead time effects. All right, so how can we mitigate the dead time effects? We group them into a few categories. We can avoid dead time effects at least a couple of different ways. We can attenuate the flux at the detector to simply make it unlikely that photons arrive during a dead period. Equipment manufacturers, vendors, and users often speak of obeying the 5% rule to do this. That means to design a system so that at most 5% of repetition periods have a photon detection. There's also a special case where the repetition period and the dead time coincide, making the dead time reduce the photon count, but not distort the histogram. This 5% number, I used this 5% number on an earlier slide when I talked about assuming that the lambda of t was low, and therefore making the distortions of the shape of the incident waveform insignificant. There's also an approximate histogram correction method in the literature that actually isn't quite exact. The third approach is to adjust the experimental conditions such that a synchronous model is valid. If the background is negligible or gating is used, the system can be forced to be reset by the time of the start of the next illumination period, and then some of these effects are diminished. But that kind of use of gating is really making your use of the incident lights less efficient. It's sacrificing the on or active period of your detector just to make your subsequent data processing easier. Our approach is to adjust the model of the scene response to be able to obtain optimal estimates despite the various restrictions above not holding. The simplest modeling of the effect of dead time is just a bias toward earlier detections. That's that little bit of a forward shift of the peak. But that's actually not accurate in free running mode. The difficulty in more accurate modeling is the lack of independence of detections in separate repetition periods. So here that's visualized with the repetition periods marked by the dashed lines and the dead periods crossing the repetition boundaries. The saving grace is that even though what happens in separate repetition periods are not independent, it's also not arbitrarily complicated. We can show that a Markov model applies. So to construct a discrete Markov chain model, we need to specify the state space and transition probability matrix. The states are defined by partitioning the repetition period based on the resolution of the time tagging. Then a row of the transition probability matrix is the conditional distribution of the next detection time given a current detection time. So what's illustrated on the right is to help us understand what goes into one of the rows of the transition probability matrix P. We're looking at the row that corresponds to a detection having occurred at the time of 20 nanoseconds. And this is illustrated for the repetition period being 100 nanoseconds and the dead time being 75 nanoseconds. So if there's been a detection at 20 nanoseconds and the dead time is 75 nanoseconds, then there can be no detections up until time of 95 nanoseconds, at which time the detector becomes active again. And so you get a probability of detection time that jumps up at 95 nanoseconds. And then everything here is reduced modulo 100 nanoseconds. So we see this detection time PDF decay after that point and wrap around as shown here. So one row of this transition probability matrix, right, it depends on the position of the actual reflector in the scene and these various parameters, the repetition time, dead time, and the detection time that we're conditioning on. Okay, and then here's another row corresponding to a detection having occurred at 40 nanoseconds. Adding 75 to 40, we get 115 nanoseconds. Reducing modulo 100, we get 15 nanoseconds. And so here, the relevant conditional distribution jumps up at 15 nanoseconds and then has the same sort of evolution forward in time. So we can generate the transition probability matrix P, and the leading left eigenvector gives us the stationary distribution of the Markov chain. So what this is telling us is that if we know the imaging conditions and these equipment parameters, then we can very accurately predict what the detection time distribution will be, including the dead time effects. So that becomes part of our forward model. And now we have, as before, an inverse problem to solve for the depth at every pixel. A more complicated inverse problem, but at least now we have an accurate forward model for it. Here, there's no electronics dead time. When you include electronics dead time as well, it does become a little bit more complicated. Actually, you have to enumerate cases depending on how multiples of the due times of dead times rank. So I'm not including that here, but it's described in an Optica paper that should come out actually this week. All right, so we experimentally demonstrated the improvement that we can get with this model. We have a ground truth proxy obtained with a long acquisition at low flux. Now, if we operate at high flux naively, there's significant bias in both the depth and the reflectivity. We can avoid dead time effects by attenuating to satisfy the 5% rule. If we do that, we're going to detect a lot fewer photons, and you can see that you maybe can't see that the bias has been removed, but you can sure see that the variance has increased. So the mean absolute error is worse. Our method is not to avoid, but instead to make good sense of the high flux data, and the results are much better. The mean absolute error of the depth is about half of what you get with the avoidance strategy, and the improved reflectivity estimation makes the visual improvement even greater. Okay, so I'm going to skip over some related stories around single photon processing. We have a recent paper that uses dithering to improve the resolution relative to the time binning in the detector. We have some other work which shows how to adapt the data acquisition. Instead of going to this extreme of saying, I'm going to continue my data collection until I have exactly one click. Instead, you can adapt the dwell time in a more interesting way and get some improvements from that. And in another recent work that came out last month, we use the equipment from a direct time of flight LiDAR system to do a particular new kind of non-line of sight imaging, where we use time of flight to infer travel distances for light, and therefore gain longitudinal resolution from that. But at the same time, we exploit the presence of occluding edges in the scene to get transverse resolution from the existence of the edge. Now, I'm going to change from problems in which we have 1 click per photon to instead having 1 click per electron. And this part's shorter. It's to reinforce the idea that particle level modeling of what's going on in an imaging system can lead to new methods, but to show you that in a different sort of problem domain. I'm going to specifically talk about helium ion microscopy, but all focused ion beam microscopy can be modeled the same way. And in fact, to some extent, electron microscopy might benefit from some of the same techniques. So I don't expect you've seen a helium ion microscope or its data. A helium ion microscope has a helium ion source and a secondary electron detector. It alternates between imaging with helium ions and neutralizing the surface charge with an electron flood gun. So we really only care about the imaging part of that, but the neutralizing of surface charge is one of the sources of improvement relative to electron microscopy. All right, the imaging is achieved by raster scanning of a beam with some fixed dwell time per pixel. The detected secondary electrons are then mapped to grayscale levels. And I guess this is the last place in the talk where there would have been a video that shows how the raster scanning proceeds and forms the image. Okay, so one major limitation of helium ion microscopy, and it's actually more significant if you look at ion microscopy with heavier ions, is the damage to the sample. Shown here is the damage to a sample caused by an incident ion beam accumulating over increasing amounts of imaging time. The main point is to say that there's really great motivation to reduce the acquisition time in helium ion microscopy because the damage that's happening to the sample through the measurement process is often what's limiting resolution. So let's see what kind of mathematical model can be generated from this physical description, and then how we might gain some advantage from new ways to process data. So we again have Poisson processes. We're going to look at the ions incident on the sample as a Poisson process. And we model that each incident ion produces a burst of secondary electrons. There's some kind of fixed dwell time, and in that dwell time, we have, because of the Poisson process model for the incident ions, a Poisson distributed number of incident ions, which we call M. And then following the tradition in this type of microscopy, we'll model the number of secondary electrons per ion as also Poisson distributed, with each burst having a Poisson parameter eta. So this gives us a model for the total number of secondary electrons, which we call Y. And since the expected value of Y is just proportional to eta, if we make an image of how Y varies from pixel to pixel, that is a reasonable image of the variation of eta. And the variation of eta is what we're trying to measure and visualize through this kind of microscopy, the variation of the secondary ion yield. But we don't want to lose sight of the fact that the randomness of the number of incident ions is a nuisance. And if we can reduce the impact of that variation, then we can do better. Okay, so the model that I just described, I mean, we can use it to write out the likelihood function. It's not the easiest likelihood to work with. Its negative log is not convex. It's multimodal. Still, we could compute maximum likelihood estimates or map or regularize maximum likelihood estimates. And this would improve upon the naive estimate of just taking the measurements y and dividing by lambda. But this gives very little improvement, and this is not the focus of what I want to talk about. There's simply not much room for improvement if we don't also change the data acquisition a little bit. Our idea here is to introduce time resolution. This is time resolution that has nothing to do with a phenomenon that is ordinarily associated with time. We're not measuring time of flight, and we're not looking at dynamics of the sample. We're introducing time resolution because it's going to make the measurements more informative in a perhaps surprising way. We use time resolution by dividing the dwell time into n sub-acquisitions. When the sub-acquisitions are short enough, we can say roughly that the number of incident ions is the number of sub-acquisitions with at least one secondary electron. That's very rough thinking. That's based on assuming at most one ion per sub-acquisition and at least one secondary electron per incident ion. So it's kind of just a plausibility argument. But this plausibility argument tells us that time resolution can essentially make the number of incident ions known. And I guess I didn't show you a variance computation, but the variation in the number of incident ions is one of the sources of error in this mode of imaging. And it seems maybe this might start to convince you that time resolution lets us fight that. The actual theory uses uses our more precise model for the acquisition without the assumptions there in parentheses. Most importantly in that, we account for the probability of an incident ion generating 0 detected secondary electrons. One of the ways to understand the advantage that we get from this time-resolved sensing is through Fisher information. We're interested in the Fisher information about parameter eta present in a measurement y. The damage to the sample is proportional to the ion dose lambda. So let's look at Fisher information per ion by dividing the Fisher information by lambda. If we do that, it turns out that low dose measurements are the most informative per ion. Also, the Fisher information is additive over sub-acquisitions, as a property of independence, which comes from properties of Poisson processes. So this variation of normalized informativeness suggests to use low dose sub-acquisitions to get the most information per unit of damage, but then enough sub-acquisitions to reach whatever quality level you want. And the simple expressions for the asymptotes on the graph that have been noted there lead to a simple expression for the overall improvement factor from this method. So let's look at some reconstructions. Here's a synthetic visual example. We use the synthetic image on the left, scaled to represent eta from 2 to 8, to generate data pseudo-randomly. And then we compare conventional and time-resolved reconstructions, and improvements are visually and quantitatively apparent. John Noddy of Zeiss also provided us with data from an Orion nanofab helium-ion microscope. We have 128 sub-acquisitions, each with low dose of 1/8 of an ion per pixel. It's achieved with a 0.1 picoamp beam current and 200 nanosecond dwell time. So on the left is what we see from a single sub-acquisition. We're not expecting, a single sub-acquisition to be enough to give an interesting image, but by our new processing of a collection of these kinds of sub-acquisitions, we want to have better imaging relative to the amount of damage to the sample. And now, the result that I'm showing on this slide, it requires some additional modeling that's omitted from the talk. In principle, a helium-ion microscope could have direct electron detection, but this particular instrument does not. So we need to additionally model the acceleration of secondary electrons to a phosphor scintillator plate, and then the photons being generated by the scintillator, amplified by a photomultiplier tube, and then detected. So it adds some extra layer of modeling, but the principle of combating the randomness of the source still holds. And we actually find that we can improve the estimated mean squared error by about a factor of 4, even more than in our idealized simulations. Again, I'll omit a related story around electron clicks. We did some work on quantum electron microscopy with interaction-free measurement. But I'll omit that. So in this talk, I've shown that simple particle level probabilistic models can lead to substantial improvements over conventional processing. The part of the story so part of this story is that fine-grained statistical modeling can make few photons or few electrons quite informative. There's another part of the story too, that one click at a time modeling is also valuable even when the signals are not necessarily weak. And I think that might be the more surprising part here. So when we include dead time in our modeling, we're getting an advantage from particle level modeling even when the signal is not weak. Actually, especially when the signal is not weak. In the helium-ion microscopy part, the advantages that I showed you actually hold uniformly over the dose. They're not advantages that are specifically for low dose helium-ion microscopy. They're advantages across all dose. So I encourage you to think about things one click at a time to see what kind of advantages might be possible. And before I invite any questions, I want to let you guys know that I have openings for both students and postdocs. If you or someone you know enjoys fun and the privilege of invention and creativity being your job, get in touch or encourage them to get in touch. At my webpage, you'll find a link to the group's YouTube channel. And now I'm happy to take any questions.
Vivek, thank you so much for a fantastic talk. Thank you very much.